Hello and welcome. In this video, we're going to take a look at rational functions. And a rational function is where we have some sort of polynomial in the numerator and some kind of polynomial in the denominator of any degree, so long as the denominator is not equal to 0. So we could talk about the domain, which we've seen before. You can't let the denominator equal 0, so that would exclude certain values from the real number line. But let's start to investigate what happens as we choose values of x closer and closer to those zeros. What's going to happen? What kind of behavior does the function exhibit as we start to get closer to those zeros in the denominator? And then let's also see what happens for very large values of x. What becomes of this fraction as x becomes infinitely large? There's lots of interesting behavior that we can take a look at. So let's start off by looking at what a rational function is. So a rational function is some sort of function of the form r of x, where it's a fraction, p of x over q of x, that are both polynomials. And of course, the bottom can't be equal to 0. All right, here we have a function r of x, and in the numerator we see a quadratic, and in the denominator we have a cubic. Now, we could take a look at the domain as being one of the many things that we would investigate about this function. And to do that, we would have to look for the zeros in the denominator, and we can do that by factoring. And we're going to do something a little bit more interesting here. We're going to see what happens as we approach those values of 0 in the denominator. Now, we're fairly lucky that we have a common factor of x in the denominator. That allows us to factor the cubic a little bit more easily. However, we could try to factor the cubic in other ways if it wasn't just a common factor, perhaps by using the rational zeros theorem and finding a 0 of the denominator and then factoring that value x minus c out, where c is some 0 of the denominator. Well, looking at the zeros of the denominator, we see the zeros are -2, 0, and 4. So the domain will consist of 4 intervals, and that will be the entire number line excluding those 3 values. Now, the question is, what happens as x approaches one of those many different zeros? For instance, what happens as x approaches -2? Well, we could try that numerically. We could take a look at values close to -2, like -1.99 and -2.01, and that would get us a decent idea. Or we can use a fairly basic concept. Whenever we have the numerator non-zero, but the denominator approaches 0, we end up with a very, very tiny number in the denominator. Now, if we take 1 divided by a very small number, that is going to give us a very large result. So applying that same concept, whenever the numerator is non-zero, if we're dividing by an infinitesimally small denominator, that means we're going to get explosively large, or it's just infinitely large. And that may or may not be positive. It could be a negative large number. We need to maybe investigate what happens. But this sort of behavior, whenever we see a 0 denominator and a non-zero numerator, this is where we have a vertical asymptote. So a vertical asymptote occurs at x equals a when we see that the denominator equals 0 at x equals a and the numerator does not equal 0. And when we factor the numerator, it's easy to see the zeros of the numerator. The zeros of the numerator here are going to be 3/2 and x equals 3. And so neither of those are the same as the zeros of the denominator. That means that at -2, 0, and 4, the denominator is 0, but the numerator is non-zero. That's when we have vertical asymptotes. So let's see what kind of behavior we get around those vertical asymptotes. We can do that by looking at a number line and figuring out if this function is getting infinitely large in the positive or negative direction as we approach 0 in the denominator. And let's start by putting the 3 holes in the domain here where we have vertical asymptotes. -2, 0, and 4. Now, remember that those aren't included in the domain. It may also be useful to see where this function crosses the x-axis, and that will be when we have 0 in the numerator. And that occurs at 3/2, or 1.5, and when x is equal to 3. So maybe we'll put dots here because this is actually going to be where we have our x-intercepts. And we can put little dashed lines here for where we see something unusual. We have vertical asymptotes. Now we can determine whether or not this function is above or below the x-axis in each of these intervals. That's going to help us determine whether or not our function goes to positive or negative infinity. Simply choose numbers within each of these intervals. A number slightly less than -2, and a number slightly greater than -2, and we'll just determine whether or not this function is positive or negative. That can be done using the factors 2x minus 3, and that factor, if you have an x value slightly less than -2, is definitely negative. Our next factor, x minus 3, if we pick a number slightly less than -2, then x minus 3 is also negative. And in the denominator, we have x. X is less than -2, then it's definitely negative. We have x plus 2. This is an important one. If x is less than -2, such as maybe -2.1, by adding 2 to that, this factor is also negative. And finally, x minus 4, and that is also negative. So on the left-hand side of this asymptote, we know that this is a negative times a negative divided by a product of 3 negatives. Overall, that gives us a negative result. And at this asymptote, we see our function is going to be getting infinitely large in the negative direction. Now, between -2 and 0, we can pick a number close to -2, but just slightly larger. But actually, any value between 0 and -2 will always have the same sign. There's no way that this function is going to change from being positive to negative or negative to positive without at least having an x-intercept somewhere in here. So we can pick any number between 0 and -2. And again, try finding the sign of each factor so that we can determine the behavior of our function. It might be easy to choose a number like -1. And you see that the only factor here that's going to change sign is x plus 2. If we pick a number that's slightly larger than -2, then x plus 2 is now positive. And we have a product of 2 negatives divided by a product of 2 negatives and a positive. And that overall is positive. Our function is going to be traveling upward. As we get close to -2 to the right, we're going to be traveling up. Similarly, a number just slightly less than 0 is also going to be getting infinitely large and positive. So we know that we are traveling upwards towards the asymptote at x equals 0. Now, we'll have to repeat this process for 1, 2, 3, 4 more intervals. Simply by picking a number between asymptotes and x-intercepts, we can always determine where this function is positive or negative. But now that we've completed the signs, we can take a look at the behavior. When we get close to the vertical asymptote, we're going to get infinitely large, and we see that we must be on the negative side here on the right. So down to negative infinity from the right-hand side of that asymptote. And then we have an x-intercept. You can see that we're going from negative to negative across these x-intercepts. Our graph is going to cross the x-axis and come back down. And then you can see, since we're back in the negative area here, as we get closer to x equals 4, we have a vertical asymptote and we're traveling towards negative infinity. But then on the other side of 4, we're back to being positive. So getting close to x equals 4 from the right, our graph is going to be getting infinitely large in the positive direction. This gives us a pretty good idea of what the sketch of this graph would look like. In fact, we can compare this to the actual graph of this using Maple. And here is that graph, and you can see the same sort of behavior. We have these vertical asymptotes, the values x equals -2, x equals 0, and x equals 4. And then we also have a couple x-intercepts here. It only just barely crosses the x-axis there, but we do have 2 x-intercepts. Now, if we want to use a little notation here, we can use an arrow to say something approaches a value. So we could describe the behavior around x equals -2. We could say that as x approaches -2, well, we have two kinds of behavior as we approach -2 from the left and from the right. We want to say as x approaches -2 from the left, we'll be approaching it from the negative side, so we'll just indicate that with a little negative sign as a superscript. That means as x approaches -2 from the left. Then the function r of x is getting infinitely large in the negative direction. We would say r of x is approaching negative infinity. Now that's not a value it's approaching, it's just a concept. It's getting infinitely large in the negative direction. We can also say as x approaches -2 from the positive side, from the right, the function r of x is getting infinitely large in the positive direction. So we say r of x approaches infinity. And that will give us at least an idea about how vertical asymptotes behave. Now, what if we happen to have 0 in the denominator and 0 in the numerator? Well, in those cases, we can cancel common factors. But remember that that does leave a hole in our function, and that can end up being either a vertical asymptote or literally just an open hole in an otherwise nice looking function. In this example, we have a function which is just a nice easy quadratic over a linear. And we can factor this fairly easily, and we can cancel a common factor of x minus 2. Before we cancel that, it's important to remember that currently the function s of x does not have 2 in the domain. X cannot equal 2. But canceling that, we'll end up with just a nice linear function. And so the graph of s of x is really just exactly the same graph as the graph of x plus 1, except it excludes a value on that graph when x is equal to 2. And so it gives us an idea how this graph would look. The graph of x plus 1 has just a nice straight line with a slope of 1 and a y-intercept of 1. So, fairly nice looking graph, except x cannot equal 2. That means we actually have to have a little hole here at the value where x is equal to 2. Not an asymptote because that single factor in the denominator canceled right out. If we had repeated factors in the denominator, or we have additional factors of other x minus c's in the denominator there, then we'll end up with additional asymptotes. But here, after canceling, you can see that we don't have any situation left over where we can possibly have 0 in the denominator. So it leaves us with a hole. Now, let's take a look and see what happens to rational expressions. Instead of taking a look at when it gets close to 0 in the denominator, what happens as x just gets generally extremely large? And we already know that 1 over a small number is very big, but what happens when we start getting large numbers in the denominator? When we're looking at a rational function, r of x equals p of x over q of x, what happens as x gets extremely large? Well, we know the bottom is going to get very, very big. And we can always use the same sort of concept. 1 over a very large number is going to get very, very small. 1 divided by a million is very close to 0. So if the denominator is going to get extremely large while the numerator stays relatively small, we have this same idea. A small number over a very large number is going to get very small and closer to 0. But in many cases, you're going to find that the numerator is also getting infinitely large, and so is the denominator, and there's some sort of relationship there. Any case where we see that as x gets very large, this rational expression at least approaches some sort of fraction, then we call that a horizontal asymptote. If we ever just let x get infinitely large, either positive or negative, and the value of some function approaches a number b, and we say that y equals b is a horizontal asymptote. And there's a few cases that we can consider whenever we have a rational expression. And it really depends on which of the two functions gets larger, p and q. If q gets much, much larger than p, well, then we have the idea that 1 over a very big number is small. And so when the degree of the numerator, p, is less than the degree of the denominator, we would say that this value of r of x is approaching 0, and we have a horizontal asymptote at y equals 0. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote of r. Now, we could also have that both of these functions, numerator and denominator, are both getting infinitely large at roughly the same rate. And that would be if the degree of them are equal. If the two degrees are equal, then it's really up to the leading coefficients to tell us what the ratio of numerator to denominator is going to approach. The horizontal asymptote in this case would be something of the form a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. All of the remaining terms are insignificant when we take a look at really just the highest power. And it's the number or the coefficient in front of those terms that's going to dictate what the horizontal asymptote of the function is. Now there's one more scenario, and that is when the numerator gets much, much larger than the denominator. If that happens, we get a very big number in the numerator divided by a smaller number in the denominator. And that's just going to get infinitely large. Something that keeps getting larger can't just approach a fixed value. It can get as large as it wants, and we don't end up with a horizontal asymptote. So to give a quick example of each of the three cases, we can just take a look at any generic polynomial in the numerator and the denominator. If the degree of the numerator is less than the degree of the denominator, such as in the case of 2x to the 4 plus 3x squared plus 5 over x to the 5 minus 2x minus 1, we really don't have to worry about any of the terms with smaller powers and really only have to look at the leading terms. And that gives us the degree. The biggest term in the numerator is going to have this x to the 4. And the biggest term in the denominator is going to have x to the 5, and it's going to win. So that means that the denominator gets much, much larger than the numerator eventually. And this is going to have a horizontal asymptote of 0, since the bottom is far outweighing the numerator, and 1 divided by a big number is very small. If the degrees are equal, then we only have to look at the leading coefficients, such as in the example 2x minus 3x cubed over 6x cubed plus 2x plus 3. We only need to look at the terms with the highest powers, and the leading terms here both have x cubes. And if they both tie, then we just need to look at the leading coefficients, negative 3 over 6. So in this example, negative 3 over 6, or simply negative 1/2, is a horizontal asymptote. And anytime that the degree of the numerator is larger than the degree of the denominator, such as in the example 3x cubed minus 1 over x squared plus 5, then the leading term here, x cubed, is going to be far larger than the leading term x squared in the denominator. And that is not going to end up with any kind of horizontal asymptote. It just gets infinitely large. We can talk about the end behavior of this function either pointing upwards or downwards, but not getting flatter and tending towards some constant. So there's no horizontal asymptote in this example. Now there is one other kind of asymptote that we could talk about, and it's not vertical, it's not horizontal, it's called a slant asymptote. And that can happen when we have a rational function where the degree of the numerator is higher than the degree of the denominator, and we decide that we want to just perform polynomial division to simplify. If that's the case, and the quotient ends up being linear, so that we may have a remainder, the linear component of that quotient is actually going to dictate a little bit about the behavior. It's a line. It's not necessarily a vertical or horizontal line. It's going to be a slant. And the function is going to get closer and closer to that line as x gets larger. And I'll show you an example where that can happen. Here I've got a function with a simple quadratic in the numerator and a linear in the denominator. You can see, well, our vertical asymptote here is going to be potentially at x equals 3. Now, if you want to double check that, make sure that you know that the numerator is not 0 at 3. So we'll factor the top and see what we end up with. Okay, now factoring the numerator, we have x-intercepts of 5 and negative 1, and you can see that we have a vertical asymptote at x equals 3. As far as a horizontal asymptote, though, we don't have any because the degree of the numerator is larger than the degree of the denominator. Now, try some polynomial division here and see if we can simplify that. You could use long division or synthetic division. And whichever method you choose, we can see that r of x can be then written out in a little different form. It can be written out as the quotient x minus 1 with a remainder of 8 over x minus 3. And that's equivalent to the original expression, x squared minus 4x minus 5, all over x minus 3. Now, what happens as x gets infinitely large? We could say, as x approaches infinity, to represent x getting infinitely large. And taking a look at the only rational expression we have left, 8 over x minus 3. The degree of the numerator is 0. The degree of the denominator is 1. Since the degree of the denominator is larger, we can see that this is approaching 0. 8 over x minus 3 approaches 0. And so, as we get farther and farther away from x equals 0, and we get farther and farther to the right, this little piece is getting infinitely small. And that leaves us with what is essentially just the graph of x minus 1. And that is a line. It's just a line with a y-intercept of -1 and a slope of 1. And we call this a slant asymptote. And that is a line that this function is going to get closer and closer to. It gets closer and closer just to this line y equals x minus 1. Not getting closer to a number, but the function itself, if you were to graph it, is going to look more and more like that straight line for very large values of x. And that is the same case as x gets very large in the negative direction. What does the graph of this thing look like? Well, we can see that we have a horizontal asymptote at x equals 3. And you could try plugging a number in on either side. You could try values that are just a little bit less than 3 and a little bit larger than 3. And we already know that this graph here crosses the x-axis at -1 and +5. So go ahead and see if you can do a little sign chart here. You should see from a sign chart that as x approaches 3 from the left-hand side, we end up getting infinitely large in the positive direction. And as x approaches 3 from the right-hand side, x gets infinitely large in the negative direction. Now, what about this slant asymptote? Well, that would be the line y equals x minus 1. And so it has an x-intercept of -1 with a slope of +1, something kind of like this. And so our graph is going to be close to that line and jump off to infinity going through the x-intercept, and going through the x-intercept on the other side, it'll approach that line. And if we zoom out far enough, it should look very, very linear. That is how a slant asymptote works. It tells us that the end behavior of this function is essentially linear. All right, well, that's a lot to take in. That's vertical asymptotes, horizontal asymptotes, and slant asymptotes. And investigating the behavior of a function as we are approaching some number or as we are getting infinitely large, that's kind of verging into the realm of calculus. So don't be too intimidated. This is actually quite a difficult topic. However, we've broken it down to some fairly straightforward rules. If you end up with 0 in the denominator and non-zero numerator, you have a vertical asymptote. If you end up with x getting infinitely large, we've broken that down into sort of 3 cases as to when you might have a horizontal asymptote. And then there's one sort of scenario that if we do polynomial division and our quotient is linear, then our end behavior is linear, and that's a slant asymptote. So if you keep it kind of simple like that and just follow the rules, you kind of get an idea of what these functions would look like. Well, thanks for watching, and I'll see you in the next video.